Namaste to all. This is Dr. B. Amudhambigai, Associate Professor, PG and Research Department of Mathematics, Sri Sharada College for Women, Autonomous Salem 16. Today we are going to see a topic in the subject mathematical modeling, and the topic to be discussed here is population dynamics model. Now let us see the application of mathematical modeling in population dynamics that can be explained through the model known as prey-predator model, and its alternate name is Lotka-Volterra model. That's a mathematical representation of the interactions between predator and prey populations in an ecosystem. Predators are organisms that hunt and feed on other animals, while prey refers to the animals that are hunted and consumed by predators. Tiger is an example for predator because it is an organism that hunts and kills other organisms for food, while deer is an example for prey because it is an organism that is hunted and killed by other organisms for food. So, on studying about predator and prey, we can say tiger as a predator and deer is a prey. Now, let us see how to explore the key components of prey-predator model that is represented by these two Volterra equations. dn by dt equal to Rn minus A into Np, dp by dt equal to minus Sp plus B into Np. Here N represents the total population of the prey and P represents the total population of the predator. So the population rate of the prey is calculated with respect to time by using the quantity dn by dt. At the same time, the population rate of the predator with respect to time is marked by dp by dt, and in order to calculate these two equations, we need to consider the intrinsic growth rate of the prey that is marked by r, and the intrinsic growth rate of the predator which is marked by a, as well as the death rate of the predator which is marked by s, and the death rate of the prey marked by b. This is the general form of um, the prey-predator model, in which the growth and the population rate of the prey as well as the predator can be calculated by using these two equations. Let us see the same by using an example as given here. Let x of t and y of t be the populations of the prey and predator species at time. In order to do such a predator-prey model, we need to make some assumptions at first. That means, if there are no predators, the prey species will grow at a rate proportional to the population of the prey species. Second assumption, if there are no prey, the predator species will decline at a rate proportional to the population of the predator species. Suppose there is an interaction between the predator and prey, then we can have the third assumption, that is, the presence of both predators and prey is beneficial to the growth of predator species and is harmful to the growth of prey species. Because of the interactions, the predator species will be increased, at the same time the prey species will be decreased at rates proportional to the product of two populations. Hence, by using these three assumptions, now we can form the following nonlinear first order differential equations, that is dx by dt and dy by dt. Of course, here x represents the total population of the prey, y represents the total population of the predator. Now we are going to calculate the population rate of the prey with respect to time, that is marked by dx by dt. At the same time, we are going to calculate the population rate of the predator with respect to time. Before calculating these two equations, we need to remember that whenever the count of the prey or predator is increased, the quantity to be assigned a positive sign. Whenever the population count of the prey or predator is decreased, associated sign will be a negative sign. At the same time, here A represents the prey's growth rate, B represents predator's growth rate, and small p represents predator's death rate, as well as Q represents prey's death rate. Otherwise, how many new predators are produced per consumed prey. By keeping all these points in our mind, let us see how to frame the equation dx by dt. Dx by dt means population rate of the prey with respect to time. So this can be calculated by counting the population of the prey in two different methods. On one thing, at one time the prey count will be increased, and another thing when the prey count will be decreased. According to our first assumption, if there are no predators, definitely the count of the prey will be increased. The count of the prey can be calculated by using the first quantity as given here, that is AX. AX means the total population of the prey to be multiplied with the growth rate of the prey. So we consider here AX, and then the count of the prey will be increased in this case. That's why we assign here a positive sign. At the same time, we need to consider the alternate case when the count of the prey will be decreased. So when the presence of the predators, automatically the count of the prey will be decreased. If there is an interaction between the predator and prey, definitely that will be a harmful effect to the prey. At the same time, the predator count will be increased. So whenever the predator count is increased, according to the count, the number of prey will be reduced. Therefore, depends on the birth rate of the predator to the interaction. Whenever there is an interaction between the predator and the prey, depends on the birth rate of the predator, the count of the prey will be decreased. Therefore, we need to consider there the product of the two species. That's why here we consider xy and x into y, that is the product of the two populations is considered, and here the birth rate is to be assigned b into xy to be calculated. But in this case, the count of the prey will be reduced as it is a negative quantity. We need to subtract the same quantity from the total count of the population of the prey increased in that year. Therefore, total population of the prey increased and total population of the prey decreased to be considered simultaneously. That's why we consider here AX with a positive sign and BXY with a negative sign. So dx by dt is calculated by using the expression AX minus BXY, in which x is a common thing which can be taken outside. Then within a bracket we can have the quantity a minus by, where both a and b both are countable quantities, so definitely they must be assigned a positive sign. That's why we are having here a comma b greater than 0. Similarly, we can calculate dy by dt, which refers the population rate of the predator with respect to time. Here also we need to consider the both cases, when the population of the predator will be decreased as well as when the population of the predator will be increased. So according to the second assumption, if there are no prey, definitely the predator count will be decreased. So there we can consider minus py, that means the total population of the predator y to be multiplied with the predator's death rate. As it is the quantity where the predator count is decreased, we need to assign here a negative sign. So minus py is considered. Then, if there is an interaction between the two species according to the third assumption, then definitely in this case the count of the predator will be increased. Therefore, we can consider plus q into xy, where q represents how many new predators are produced per consumed prey. So according to this case, the count of the predator will be getting increased. Therefore, there we need to assign a positive quantity. That's why we consider here plus q into xy. Another thing, if there is an interaction between the two species, only in that case we need to multiply the population of the two species. Therefore, only in such cases we need to consider the total population in the format of x into y. That's why in the second term we are having q into xy. So on the right hand side of dy by dt, minus y is a common thing which can be taken outside. Then within a bracket we can have p minus qx. Of course, here also p and q are countable quantities. Therefore, we need to assign them positive values. P and q must be greater than 0. Now, we are going to calculate the equilibrium sizes of the population. Equilibrium sizes means when there are no changes in the rate of change of the population of prey, as well as there are no changes in the rate of change of predator population. So when will it happens means whenever there are no changes means definitely dx by dt equal to 0 and dy by dt equal to 0. If dx by dt equal to 0, then on equating this expression to 0, what happening? When we consider dx by dt equal to 0, we get that a into ax minus bxy equal to 0, in which x is a common quantity, can be taken outside. Otherwise, ax equal to b into xy, we are getting x can be cancelled, and finally we can have a by b equal to y. So on calculating the equilibrium size of the population, we need to consider dx by dt equal to 0 as well as dy by dt equal to 0, because in case of equilibrium position, the count will be at stable stage. There will not be any change in the rate of change of population of the both the species. So in that case, dx by dt equal to 0 as well as dy by dt equal to 0. On equating dx by dt equal to 0, we are getting y is equal to a by b. So we can say equilibrium size of the predator will be a by b. Similarly, we can calculate the equilibrium size of the prey by considering dy by dt equal to 0. On equating dy by dt equal to 0, similarly we can get x equal to p by q. As they represents the equilibrium sizes of the populations of prey and predator respectively, they are also marked by xe and ye respectively as shown in the third equation. So, if the initial populations of the prey and predator species are p by q and a by b respectively, then the populations will not be changed with respect to time. Of course, there will be another possibility to get the equilibrium size, that is none other than the initial populations, that is x is equal to 0 and y is equal to 0. Even in that case also, we can have the equilibrium position of the two populations for both predator as well as for prey. Now let us calculate dy by dx, that means which is calculated by considering dy by dt whole thing divided by dx by dt, and hence we can get dy by dx in this format minus y into p minus qx divided by x into a minus by. Now we are going to solve this differential equation by using our initial population. Of course, we are taking here the initial population in the form x naught and y naught. X naught means x of 0. That means initially at the time t equal to 0, the population of the prey is taken in the format x naught and at the time t equal to 0, the population of the predator was taken in the format y naught. Why not? Now, let us see how to solve them and how to get the differential equation, how to get the final solution of the differential equation. See, we are considering here dy by dx, and that is equal to minus y by x into p minus qx divided by a minus by. In order to solve this differential equation, we need to cross multiply them. That means we are going to apply the variable separable method. And so we are collecting the terms with y on the left hand side and terms with x on the right hand side. Later, let us consider each term separately, that is a into dy by y on the left hand side. On the left hand side, the second term will be minus by into dy by y. On the right hand side, minus p dx by x, minus into minus, plus qx by x dx. Then, in order to solve the differential equation, we need to remove the differential operators, which can be done successfully by integrating them on both the sides. So let us integrate them on both the sides. On the left hand side, first expression is a by y into dy. So on integrating this expression, we are getting a into log y, because we know the familiar formula, integration of dy by y equal to log y, and then minus, in the second term we are having b into dy under the integral sign, where b is a constant that can be taken outside, then minus b into y. On integrating the second term, we get this one. Similarly, on the right hand side, we get minus p into log x plus q into x. And always on integrating any such quantities, we used to put one constant, and let us consider the constant here in the form c. Let us consider the constant here in the format of c. Now we are going to derive the constant value by considering, by applying the initial conditions what we have considered already. The initial conditions are x of 0 equal to x naught and y of 0 is equal to y naught. So let us consider the initial conditions here, that is x of 0 is equal to x naught and y of 0 is equal to y naught. When applying these conditions here, we get a into log y naught minus by naught equal to minus p into log x naught plus q x naught plus c. And so we got here the value for c in the second equation. Let us apply the value of c obtained in the second equation in the first equation number 1, so that we can eliminate the arbitrary constant c from the first equation. So finally we get a log y minus by equal to minus p log x plus qx. There we can substitute the value of c as we got from the second equation, that is a log y naught minus by naught. Other two expressions minus p log x naught and plus qx naught to be taken to the left hand side on substituting the value of c. That's why here we get plus p log x naught minus qx naught. Later we can combine the like terms, that is a into log y minus log y naught plus p into log x minus log x naught, that is equal to b into y minus y naught plus q into x minus x naught. Finally, we can combine the log terms. So we get the final solution as we have obtained here, that is a into log y by y naught plus p into log x by x naught equal to b into y minus y naught plus q into x minus x naught. So this is what the solution of the differential equation what we have obtained in equation number 5. So the final solution we got now in the format of a into log y by y naught plus p into log x by x naught, that is equal to b into y minus y naught plus q into x minus x naught. On seeing this expression, equation number 6, we can identify that every point of the first quadrant of the xy plane, and through every point of the first quadrant of the xy plane, there is a unique trajectory. Trajectory means that is the curved or straight path traced by an object or particle as it moves under the influence of forces. For example, gravity is an example for a trajectory because of the expressions we got in sixth equation, where the expressions of x and y are not interconnected. They are obtained separately in each term. Because of that reason, we can conclude no two trajectories intersect, since intersection will imply two different slopes at the same point. So, from the above expressions, we can have the following discussions. That means, if we start with 0, comma 0, or the equilibrium positions P by Q, comma A by B, we get point trajectories. If we start with x is equal to x naught and y is equal to 0 from equations 1 and 2, the equations 1 and 2 are given here in the formats of dx by dt as well as dy by dt respectively. From them we can find that x increases while y remains 0, because in equation number 1, expression of y having a negative sign. Therefore, we can conclude x increases while y remains 0. Similarly, if we start with x is equal to 0 and y is equal to y naught, we find that x remains 0 while y decreases. From the above from the equations 1 and 2, this is true that the positive axis of x and y give two line trajectories as shown there in the equation number 3.1. On every stage, the expressions of x and y obtained in the solution are not met at any cost. Therefore, the trajectories are given independently as shown here. So, this is an example for such trajectories. So, we can consider no two trajectories intersect as no two trajectories intersect. No trajectory starting from a point situated within the first quadrant will intersect the x-axis as well as y-axis trajectories. So on extending such a trajectories, the trajectories will not meet the x and y axis. Definitely, they will be circulating independently as shown there in the figure. Thus, all trajectories corresponding to positive initial populations will lie strictly within the first quadrant. Thus, if the initial populations are positive, definitely the output will be positive. That means the populations will be always positive. If the population of one species or both the species are initially 0, then it will always remain 0, because you could see the expressions given here in equations 1 and 2. Dx by dt is expressed in terms of x, dy by dt is expressed in terms of y. Whenever x is equal to 0 or y is equal to 0, simply we are getting that dx by dt equal to 0 and dy by dt equal to 0. Because of that reason, we can say if the initial population of one species or both the species is initially 0, then it will always remain 0, because there will not be any change in the expressions of dx by dt as well as in dy by dt. We can also extend our discussions by considering the expressions on four different quadrants as shown here. The lines through P by Q, A by B, parallel to the axis of coordinates, divide the first quadrant into four parts: 1, 2, 3 and 4. Using the equations 1 and 2, we can also say that the following following results. That means in result number 1, if dx by dt is less than 0 and dy by dt is greater than 0, definitely dy by dx will be less than 0 because we get dy by dx on dividing dy by dt by dx by dt. So if any one of them is negative quantity, definitely dy by dx will be a negative quantity. In a second result, we can say dx by dt is less than 0 and dy by dt is less than 0. That means both the expressions dx by dt and dy by dt are negative. Then definitely dy by dx will be a positive quantity because minus divided by minus will be a positive quantity. In third part, we can say whenever dx by dt is greater than 0 and dy by dt is less than 0, definitely dy by dx will be less than 0 as dy by dx is obtained by the quotient of both the dy by dt and dx by dt. Finally, in fourth part, if both the expressions dx by dt and dy by dt are positive, then definitely dy by dx is also a positive quantity. Because of these results, we can say the direction field at all points shown in the trajectory figure. Each trajectory is a closed convex curve and these trajectories appear relatively cramped near the axis. So we could see the cramping through the figure, and also in part 1 and 2 prey species decreases, and in part 3 and 4 it increases. Similarly, in part 4 and 1, predator species decreases and in part 2 and 3 it decreases. After a certain period, both the species will return to their original sizes and thus both species sizes will vary periodically over time. Because of these discussions, we can conclude the model serves as a valuable tool for understanding the intricate dynamics of prey-predator relationships within ecological systems. Also, it provides insights into population fluctuations and ecosystem stability over time. So, by studying such predator-prey models, prediction such predator-prey models predict dynamic patterns like stable equilibrium, oscillations, or extinction, helping students to understand ecological interactions and population dynamics in simplified systems, offering insights applicable to real world ecosystems and resource management. Thank you.